Hello friends, this video on Chemical Kinetics part 3 is brought to you by examfear.com. No more fear from exam. Now let's talk about the unit of the rate of reaction. See, rate of reaction is what? Is either minus of change of concentration of product by time or change of concentration of reactant by time. If you talk about the unit now, unit of rate of reaction, let's put the unit of product. So what is the unit of concentration of product? See, concentration is always in moles per liter, molarity, correct? And delta T is a time. Time can be in second, minutes or hour. Generally we use second. It can be minutes also, it can be hours also. And this is for the gaseous state, sorry, liquid state. Liquid state we have moles per liter. So for the unit of reaction for the liquid state will be moles per liter per second. Right, this will be moles per liter per second. That will be the unit of reaction for the liquid state. If you talk about the gaseous state, in gaseous state, let me talk about the gaseous state. In gaseous state, what happens is the concentration is in the, let me draw a line here, is in the atmospheric pressure, ATM, and time will be in second. So this will be the unit of rate of reaction in gaseous state. Is this clear? So we have two different type of rates, instantaneous rate, average rate. In both the case, the unit is same. It is, if it is a liquid solution, we'll talk about moles per liter per second. That will be the unit of rate of reaction. If it is in gaseous state, for example, H2 plus O2. So in that case, we'll talk about atom per second. ATM is nothing but atmospheric. Let's take this example. We have to find the average rate of reaction during the time interval. This is my butyl chloride reacts with water to give butyl alcohol and HCl. Concentration of butyl chloride is given for given time interval. Right? So you plot the graph also. What if it at 0, the concentration was 1. At 50 it is 0.095. Somewhere leave 50 we have 200. It is 0.067. Somewhere here. At 300 is 0.05. 300 is 0.05 somewhere here. 400 is 0.04 somewhere here. 700 is 0.02 somewhere here. And then 800 is 0.017 somewhere here. Yeah. So if you see, this is the kind of graph you get. But the question is, they don't want us to draw the graph. They asking for the average rate of reaction during the time interval. All this interval. This is one interval. So other interval is this, like that. So let's find the first time interval reaction rate, right? AVG rate is nothing but UC minus of change of concentration of product. That is, this is the final concentration. 0.0905 minus initial concentration 0.1 by change in time is 50. You solve this, you get 1.90. Correct? Let's do it for the next time interval. This is the interval, next time interval. So here again my rate is nothing but minus of final concentration, that is this 0.0820 minus initial concentration will be this one 0.0905 divided by time will be 100 minus 50, that is 50. You solve this, you get something as 1.7. Correct? Let's talk about the third window. Here we'll talk about the rate once again. minus of final concentration is nothing but 0.0741, initial is 0.0820, by time is 150 minus 100, it is 50. You solve this, you get 1.58. You keep solving it, you see that the rate is decreasing. It's 1.9, 1.7, 1.58. The next will come out to be 1.4. Then it will be 1.22. You can solve it. Then it will be 1.1, 1.04, and the last will be 0.4. You see the rate of reaction is decreasing. So the main point why we took this numerical was to show you that for a given reaction, the rate of the reaction decreases, it slows down, and then it reaches equilibrium. That's what happens. Initially, the rate of reaction is more, then the concentration of the reactant goes down because it is being consumed, and now it is in the product form. The rate of the reaction is decreased. To design the expression of the rate of reaction, let's take this reaction. I have my Hg plus Cl2 gives HgCl2. This is the liquid, chlorine gas, HgCl2 in solid. So you see the rate of reaction here. It will be what? Minus of change of concentration of Hg with respect to time, or minus of change of chlorine, concentration of chlorine with respect to time, or plus of change of concentration of HgCl2 with respect to time. Correct? This is in the product side, so plus, these two are in reactant side, so negative. Fair enough. Now let's consider another reaction. We have, let's suppose, nitrogen that reacts with 3 moles of hydrogen to give 2 moles of NH3, all in gas form. Now if you see the stoichiometric coefficients of the reactant and products are not equal to 1, they are not same. So in this case, the rate of disappearance of any reactant or the rate of appearance of product has to be divided by their stoichiometric coefficient. So in this case, if I want to write the rate of reaction, nothing but minus of change in concentration of N2 with respect to time, minus of change of concentration of H2 with respect to time. Here there is 3, so I'll divide it by 3. Or plus of change of concentration of NH3 with respect to time. Here you have 2, so I'll divide it by 2. Here was 1, so 1 divide multiply doesn't make any difference, so nothing is here. Now you must be wondering why there is 1 by 3 here, 1 by 2 here. There has to be reason, right? There has to be reason why we have divided with this stoichiometric coefficient. So let's see, let's assume at t is equal to 0, this was x, this was y, and this was z moles. At t is equal to t, this becomes x minus 1, let's suppose. So this becomes what? Y minus 3, correct? Because since it is 1, this is 3. If 1 moles of nitrogen is getting consumed, 3 moles of hydrogen has to get consumed, and this becomes z plus 2, because if 1 mole of nitrogen is getting consumed, 2 moles of ammonia will be produced. Correct? So let's find the value of first delta N2 by delta T here, minus of this. This becomes minus of delta N2 is what? Final concentration, initial concentration. Final concentration is x minus 1 minus initial concentration is x divided by change in time is t. And this becomes, if you see, 1 by. Correct? Let's find for this. Minus of change in concentration of hydrogen. Final concentration is y minus 3. Initial concentration is y by t. And that is nothing but 3 by t. Let's find for these values. Change in concentration of NH3. Ammonia final concentration is z plus 2. Initial is z. Final minus initial by t. Cancel. That is 2 by t. So if you see, this is 1 by t. This is 3 by t, this is 2 by t. They are not same. They can be made same if you multiply this by 1 by 3 and 2 by t with 1 by 2. So in this case, if you see, all becomes 1 by t. Correct? And that is the reason why we divide all these values by their stoichiometric coefficient. See, for gaseous reaction, It may not be moles per liter. We can we can denote the concentration using pressure, the partial pressure actually, the partial pressure of the reactant and product. Okay. So let's see this reactions. I have 2HI and it gives hydrogen and iodine, all gas. For this I want to write the rate of reaction. Just practice minus of, since it's the reactant, change in concentration of HI by delta T, and since there is a 2 here, I'll multiply 1 by 2, or this is nothing but this is a product now, change in concentration of H2, no negative sign because it's a product, it's 1 here, so I can just say by T, or change in production concentration of iodine by delta T. Correct? Let's take another example just for practice. Let's suppose I have 5. यार क्या हो रहा है यार, इतना जल्दी क्यों हैंग हो रहा है सब. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.